Thank you very much, Karen, for the kind introduction. Thank you, everybody, for coming for my talk. So today my talk will be focused on heterogeneous catalysis and X-ray absorption spectroscopy. And the main idea of the talk is to convince you that X-ray absorption spectroscopy is quite unique tool for the uncovering active sites in heterogeneous catalysts. And the beauty of this technique is in many senses, but in particular because you can look at uncover the structure of active reactivity of active sites without any material or pressure gap. So this is a big advantage. And so the talk will be structured in the following way. First of all, I will introduce you, just remind you the basic concepts of catalysis. Then we'll explain basic principle of X-ray absorption spectroscopy, which is relevant for the catalysis research. And the main part of my talk will be showing you our research examples of my group in particular, where we used this X-ray absorption spectroscopy to get much more information about the structure of active sites and reactivity. So first of all, catalysis, all of you know that like the basic definition of a catalyst is a substance which allows chemical transformation, but during this transformation it's not being consumed. And it's not being consumed, not because it does not react, actually it reacts. It binds, oh, sorry. It binds reactants, it performs the reaction, and but then it separates from the products, which allows to perform let's say many times this so-called catalytic cycle. And also what is common knowledge that the catalyst, it offers some alternative reaction pathway to allow to transform reactants into products with less energy and to in specific direction, let's say. So this is very important. And it's let's say it's useless to remind you that why catalysis is so important in our society, because catalysis is in the basis of all chemical industry. Because and in particular nowadays, when let's say we face challenges of sustainability, of pollution, and scarce, let's say, resources. Therefore, the catalysts need to become even more efficient. They should use less critical elements and, let's say, allow life of so many people on the earth. Because the catalysts are helping to produce fuels, fertilizers, let's say the heating or for manufacture. It's important to use catalyst. It's important for also for pharmaceuticals. So it's many in all chemicals. Basically, they need catalyst. And what are heterogeneous catalysts? So heterogeneous catalysts are the catalysts which are typically desired by industry, because they are typically solids, which with very high surface area, which contain typically metals or metal nanoparticles, or some clusters, or even atomically dispersed species. And this, let's say, and these metals are supported on very high surface area supports, which is around 100 square meter per gram, because, let's say, these catalysts are supposed to react solid catalysts react with gases or with liquids. And it's why industry likes a lot heterogeneous catalysts, because it's very easy to separate gases and liquids from solids. And therefore, heterogeneous catalysts are very typical in industry. However, the structure of catalyst, of this heterogeneous catalyst can be very complex, because it can be very disordered structure, difficult to sometimes to control, not periodic. Moreover, it can evolve during catalysis, and understanding which part of the material making active species is crucial for the rational design of beta catalyst. And now it comes X-ray absorption spectroscopy. So X-ray absorption spectroscopy is a method which is currently used a lot in catalysis research for the uncovering the structure of active sites. And why it is? Because this, let's say, it uses basic principles of interaction of X-rays with matter. You know that X-rays, they interact with matter, or they can be or elastically scattered from the electronic clouds, or they can be resonantly absorbed. And this resonant absorption, it happens when the energy of incident X-rays is above the energy of the binding energy of electron on the shell. And if the absorption process happens, X-ray kicks electron from its shell. Of course, let's say very soon in femtosecond, let's say this hole is being filled, but basically we can measure the probability of this absorption and detect not only the concentration of the element in the sample, but also its assesses its chemical state. Because, let's say, why the technique is element specific? Because, as you know, each element it contains a specific electrons are situated very specifically on its level. And then if material contain many elements, by tuning, having tunable X-ray source like synchrotron, you can resonantly measure the absorption edges of the different edges and different elements. So, for example, how in the easiest situation X-ray absorption spectrum can be measured, you need to place the sample containing your element of interest between two detectors. The first detector measures incident beam intensity before the sample, and the second one after the sample, so transmitted intensity. And then let's say we scan X-ray energy by moving the monochromator, and we measure for example, here it's a transmission spectrum of, let's say, transmission intensity of sample containing platinum and tin. And you can see that at certain energy, there is this threshold appearing, and they correspond to the absorption edges of this element, platinum and tin. And by doing this mathematics, let's say Lambert-Beer law, you can measure absorption coefficient as a function of energy. And this is, let's say, the basic principle how to measure X-ray absorption spectra. But this is just why actually the X-ray absorption, but X-ray absorption spectra, as you see, they also have fine structure. It's not just a simple threshold. And this fine structure is reflected by the basically the structure of the element. For example, here it's iron in the structure of iron oxide, And it is this spectrum is specific for this element in this state. And this near age fine structure is called XAS, and extended X-ray absorption fine structure is XAS. Both them of these parts of the X-ray absorption spectra, they provide chemical information about oxidation state. For example, XAS is mainly oxidation state, local symmetry, and X-ray XAS, it's mainly local geometry. While X-ray XAS also contain information about the local geometry, which is a little bit more difficult to get out. So yes, and let's say it's really chemical structure which is producing this oscillation of the absorption coefficient. Because if the element would be just in the gas phase, it will be really like a simple step and nothing else. And once we have local environment, let's say once there are neighboring atoms, the photoelectrons which are produced during X-ray absorption process, they get scattered on the neighboring shells, on the nearest neighbors, and this produces this oscillation of absorption coefficient, which can be decoded afterwards. So from the spectrum, we can get to the structure. So the main advantages of X-ray absorption spectroscopy is actually its element specificity, its sensitivity to the chemical state, and also it is sensitive to the average structure of element in the sample. So both, let's say, average structure, it means crystalline or amorphous, or whatever state is element in the sample, we get, let's say, each species will be coming with equal contribution. And then it also does not require vacuum, which is also an asset, because many chemical reactions, as you know, go at very high pressure, let's say very much above atmospheric pressure. And this is also a great asset of this technique in, let's say, for the catalytic studies. And what is also nice that nowadays, at modern synchrotrons, you can measure X-ray absorption spectra very fast. So you can measure them in seconds and minutes. So you can follow how the catalyst structure evolves over time, or how it responds to certain perturbation of the system. And this is also additional opportunity for the research to draw structure activity correlations, and to understand how the active site, how actually the catalytic cycle ultimately function. So this uncovering structure activity correlations is depicted, let's say, schematically on this slide. So let's say for example, if we study heterogeneous catalyst, we put it in a small reactor, for example, made of quartz tube. It's a powder catalyst. We send reactants through it in a gas or liquid form, and we measure the products. And if at the same time we measure products and measure, for example, X-ray absorption spectra, we come to the operando, because if we don't measure the products, it would rather be in situ. But if you measure products, it's operando. You put the catalyst exactly under conditions of catalysis, and you can see by your eyes this catalysis. And yeah, basically drawing structure activity correlations, we can understand what is the reason why one catalyst is more active than the other, what is the, let's say, why the selectivity changes, for example, over time, or for example, why the catalyst degrade, also its activity decreases or increases during operation. So after this, let's say, just basic introduction to our research, I wanted to show you our research examples, what we recently did. And I think this research example, they show what is currently possible to do. Let's say, what kind of research is possible to do, and maybe you can get also ideas what you can do about your systems. For example, first example was about selective oxidation of alcohols. In this project with Anna, who was our PhD student, we look at the reaction of selective oxidation of alcohol or of ethanol into acetaldehyde on the vanadium-based catalyst. And vanadium-based catalyst, we were looking on vanadium-based catalyst, which were promoted by titania and ceria supports. These are very famous catalysts for selective oxidation of many kinds of reaction. Ethanol was chosen like a very example where we could easily make this catalytic condition and follow, let's say, with spectroscopy, but it can be also done under different conditions. And what is peculiar about this catalyst, it is known that this, let's say, vanadium with submonolayer loading, its activity can be greatly promoted by this ceria and titania. And it is also known that oxygen, which participate in the reaction, it's actually not oxygen from the gas phase. It's an oxygen, most probably, which is, let's say, binded to the catalyst. And this oxygen, it can selectively oxidize ethanol into acetaldehyde, and some vacancy should be formed, and the charge should be compensated by the change of the oxidation state of one of the cations. So it can be vanadium, it can be titanium, it can be cerium. So we were specifically looking, so which redox couple is mediating this catalysis. So it can be vanadium 5 plus vanadium 4 plus, vanadium 5 plus vanadium 3 plus, or it can be titanium, or it can be ceria. And to be able to, let's say, pinpoint how it's going or how it goes, first of all, we will, let's say, simplify down a catalytic system, simplifying in a way, for example, vanadium on titanium, it's quite difficult to study with X-ray absorption spectroscopy to measure both elements with equal sensitivity. Because these edges are very close, X-ray absorption edges. So we were producing bilayered catalyst where vanadium with submonolayer loading was promoted by one monolayer of titania. And we could show that when it was promoted, one monolayer of titania, the catalyst was 40 times more active, and it was similar to the state-of-the-art catalyst. So the promotion of vanadium of titania was in place. So we modified the catalyst, and we also designed experiments. So considering that the process of alcohol formation is a slow part of the catalytic cycle, and process of oxidation is a long part of the catalytic cycle. We wanted to pick up which let's say redox couple is active. To do it, we decided to perform a transient experiments, basically by switching off periodically oxygen supply. And we did it in this setup where we got Operando reactor, where we put catalyst powder, sieved catalyst powder in this cell. We were sending ethanol and oxygen mixture, which we will periodically switch off oxygen supply. And we were monitoring all the time catalytic activity with infrared spectroscopy, which could measure the concentration of ethanol, acetaldehyde, and even some other, let's say, products. And we could see, let's say, once we performed this experiment, we could see that as soon we switched oxygen supply, the spectra were changing of vanadium, and then they were, when we switched on oxygen supply back, they were changing back. We perform quite sophisticated chemometric analysis of this vanadium catalyst, and figure out that all these spectra can be fitted only by three components, which were similar to vanadium 4+, vanadium 5+, and vanadium 3+. And then we were able to plot the trends, how the concentration of all these components changes as a function of time. And in the white, you see ethanol plus oxygen, and in the gray, you see where we switched off oxygen supply. We could see that when we switch off oxygen supply, all the time the concentration of vanadium 5+ was decreasing, vanadium 4+ was increasing, vanadium 3+ was not changing at lower temperature, and when we performed the same process, progressively increasing the temperature, we could see that the vanadium 3+ started also to make, let's say, to introduce its activity. Then, what was very nice with this project, that we could not only see that which element was somehow changing its oxidation state faster, we could also quantitatively measure the initial rate of formation, for example, of vanadium 4+, vanadium 3+, the rate of disappearing of vanadium 5+, and correlated on this Arrhenius plot with the rate of acetaldehyde formation. As I know, this is the only technique which allows to do such a quantitative correlation and to pick up, let's say, the reactivity of the active site, of the catalytic cycle. So we could actually see that acetaldehyde formation was more or less twice slower at different temperatures than the rate of vanadium 4+, for example, formation. Considering that it's a 2-electron process, it's really vanadium 4+, vanadium 5+ redox couple is the main actor of this catalytic cycle. As we can see, vanadium 3+ was appearing only at higher temperatures, and it looked rather like a secondary process of over-reduction of vanadium 4+. And let's say, looking at titania, we could confirm that titania was really redox inactive in this catalysis. So it was promoting vanadium, but it was not redox active itself, which in principle we expected, but now we could quantitatively see that it is really the fact. And this is going like this. And one can say, okay, this probably, it's like this would happen also for ceria, it will be exactly the same, but actually not. So I can show you how it was for ceria. So for ceria, we made a bigger series of the catalyst, where we could, we varied the concentration of vanadium on ceria, the surface density, and we measured the catalytic activity. And we could see that actually ceria alone was already active for this selective oxidation. It was not so selective, but it was active. And then we, let's say, increasing the concentration of vanadium up to 0.3 monolayers was improving the performance of the catalyst in terms of activity and selectivity, and going above was decreasing. This, let's say, this we also wanted to investigate. Besides which redox couple is redox active, we also wanted to see why, let's say, this catalyst with this loading is the most, is the best one, to find some rational explanation. So we perform again this oxygen switching experiment. So it's also, and what we could see was quite interesting. So we could perform, here you can already see that we measured both redox activity and vanadium and cerium. So cerium redox activity is shown in blue, and vanadium redox activity is showing with red. Here we could not, let's say, we almost never detected vanadium-3, so I will not speak about it. So for one catalyst, we could only see. So we will focus on the reactivity of vanadium-4, vanadium-5 redox couple and cerium-3, cerium-4 redox couple. So first of all, the catalyst containing no vanadium, ceria was redox active, but just a little bit. Once increasing, a little bit increasing the concentration of vanadium, it promoted a lot the redox activity of cerium, while the redox activity of vanadium also appeared. Further increasing of concentration of vanadium made increased again the redox activity of cerium, but also the redox activity of vanadium was increasing, and this was the catalyst with the best performance. Further increasing of the concentration of vanadium actually decreased the redox activity of cerium, but increase the concentration of cerium 3+, which were permanently remaining in cerium 3+ state. And basically the redox activity of vanadium was also, it was kind of slowing down, and again it's increased the concentration of vanadium 4+, which were trapped in this reduced state. So making, let's say, thinking a lot about it, we could come out with a model how it's going on. But also quite interestingly that once we look at this activity, it's actually, they follow, it's quite interesting. You cannot say which one is happening first. Vanadium reduced to cerium, they really look like they are doing simultaneously. And if you normalize them to one, you see they are exactly at the same time happening. So both vanadium and cerium seems to be part of the same active site. So the electrons are redistributed between vanadium and cerium. And depending on the ratio of vanadium and cerium on the surface, the redistribution is different. So let's say, summarizing everything, we came out with a model that, as I told you, when we add a smaller concentration of vanadium, we promote a lot of redox activity of cerium. This you see with the light green atoms, these are cerium atoms which are redox active. So their concentration increased, and at the same time, you see some of the, let's say, dark khaki, let's say, atoms appear. These are also cerium 3. These are cerium atoms which are trapped in cerium 3+ state. And the concentration of this atom is increasing a lot when you add much more vanadium, which makes the catalyst less active. It explains why there is this optimal concentration of, let's say, ratio of between optimal loading of vanadium to make the most active catalyst. It's actually about 30% of the monolayer is the optimal concentration, but also we can see that the active sites are rather complex. And once we did it on titania, we got something completely different that we got on ceria. So this extrapolation often does not work so simple. And the strength of these techniques is that you can really look at it and check by yourself. And without transient experiments, we could also never pick up which vanadium and cerium is actually active and which is not active, because this is just by when we vary it, the concentration, we change the concentration of oxygen, we could pinpoint which of the cations are redox active. So this is the beauty of the X-ray absorption spectroscopy for looking, let's say, ultimately at the structure of the reactive site. But this is not the only possibilities, of course, possibility of this method. And the second example, I will show you another type of structure-activity correlations. Here in this catalyst, in this project, let's say, which we did with our PhD student Ilya Sadikov, we were looking at the selective oxidation of CO in hydrogen flow. It is very important to purify hydrogen flow from CO because CO can originate, especially when hydrogen is produced, let's say, from fossil fuels, but also from biomass. So this hydrogen contain always impurities of CO. And how to remove the CO? Why it is important? Because CO, if we use the hydrogen in low temperature fuel cells, CO can poison noble metals. They are not performing in fuel cells as good as they would perform in pure hydrogen. So elimination of CO for this reason is very important. But but how to do it? So one of the ways to do it is a catalyst which would selectively oxidize CO into CO2 while keeping hydrogen not oxidized. And there are many catalysts. Let's say there are some catalysts in the literature suggested for it, which are extremely selective and which can reduce to, let's say, reduce to ppm levels, the concentration of CO. And such one of these catalysts is a platinum iron catalyst. So in this catalyst, while it's known that they're very effective, it's not clear, or let's say on this plot, you see that CO oxidation rate per gram of, let's say, of more expensive metal like platinum, gold, or copper in this catalyst as a function of temperature. And you can see that at the same temperature, there are many platinum iron catalysts which perform completely different. Their activity differs by orders of magnitude. And it is not clear why it happens. And it cannot only be explained by the size of the particles, because all of them, majority of them contain very small nanoparticles. And due to this, it is not clear which mechanism is in place. In the literature, it was suggested many types of active sites for this catalyst. And in particular, it's not clear in which state iron it should be to make this catalyst active. So it was suggested that it should be sometimes it's suggested it's iron 3, sometimes it's suggested it's iron 0, sometimes it's suggested that it is iron 2. For platinum, more or less, there is agreement that platinum should be metallic, but sometimes it's suggested that it should be platinum iron alloy. And to pinpoint what is active, we decided to use X-ray absorption spectroscopy. And our approach was to make the catalyst with activity similar to the best catalyst reported in the literature, and then look which, let's say, in which state iron, which iron state correlates with activity. So we made ourselves the catalyst with relatively simple method with incipient wetness impregnation. Both platinum and iron were added to silica or to alumina. And as it was also reported in the literature, it appeared that the pretreatment of catalyst under high temperature, so here you can see the formula of the catalyst plus the temperature of the pretreatment in hydrogen, and the last thing is the concentration of hydrogen. So the concentration of hydrogen had a crucial importance on the activity, because here you can see activity as a function of temperature. Here in red you see the catalyst pretreated at 400 Celsius in 5% of hydrogen. And here basically the same catalyst pretreated at at 100%, 1 bar of hydrogen. And the activity differs by really a lot, which suggests that maybe some reduced iron need to be very active. So we decided to check it systematically. Again, operando cell. In this case, we use mass spectrometer to measure the activity. And we measure X-ray absorption spectroscopy at platinum L3H and iron KH. What was important here that all the catalysts, they contain iron in actually all states. Most of the catalysts contain iron 3, iron 2, and iron 0. If you put them under steady state condition, you cannot say, let's say, all oxidation state present, which one is actually correlates with activity. Therefore, we decided to do a smart experiment. So for several catalysts, we first activated them according to the protocol, which I've shown before, depending on it can be at 5% or 100% of hydrogen. Then put them under catalytic condition. We could see that the activity was, once you put, you add, let's say, you make this prox mixture, the activity very sharply increase. And then at full catalyst, there is initial deactivation and then reaching steady state activity. And we exactly looking at this part of the experiment to try to understand which of the concentration of which iron correlates with activity, because we could each XAS spectrum we could decipher in which concentration what is the fraction of each state of iron. So we did this experiment for several catalysts, and this is the result. So we could see that the activity, we were probing how activity was correlated with the fraction of iron 2+, with the fraction of iron 0, and the fraction of iron 3. The experiment showed for several catalysts that the activity actually correlates only with iron 2 concentration. It doesn't correlate it with iron 0, and with iron 3, it's rather correlated negatively. And in spite of the fact that the fraction of iron 2 was actually not the major fraction. So in iron 2 was just up to 12%, but we could pinpoint that this is the important part of the catalyst, which makes it active, more active. Of course, other iron can be also active, but not to the same level. Which brought us to the conclusion that it needs to be iron 2+ in a close contact, of course, with platinum, because without platinum it would never work, because platinum would activate oxygen, and no, platinum would activate COR, and oxygen would be activated on this iron 2+, which is connecting oxygen and very fast reacting with COR. So the resting state of the catalyst is of iron in the catalyst is iron 2+. And most probably the mechanism of deactivation of the catalyst is the formation of the species similar to iron 2 or 3, because we could see that once it goes there, you need again activation in hydrogen, and only this can, let's say, make it again active. So later we also look at the role of water in this formation of the active site, and this is also very interesting part. So when the steam, or when the catalyst is initially wet with liquid water, like impregnated with water, or activated in hydrogen with a steam, you can make even more active catalyst. So you can see, depending the same catalyst, depending on the activation procedure, you can increase a lot the activity. And we look again how the iron 2+ was correlating with the activity. And we could see that for different catalysts, we could get different slopes of, let's say, this correlation. So all catalysts showed correlation, but with different slopes. And the higher the slope, the higher the activity of these sites, because per atom of iron there is more, let's say, turnover frequency is increasing. So we could also demonstrate what is the reason of this activation with the presence of water. Basically, it's most probably it's formation of some oxyhydroxide on the surface, which is even more active than just iron oxide. Of course, this it can form also, some of it can form also without any additional water, but the quantity of it tremendously increase when you add water during the pretreatment. So this is also something that we could explain many trends for this catalysis. And the last example, I will not spend on it too much time because I think I'm already speaking a lot. So this is, let's say, we decided to go, let's say, also to more complex catalysts. Let's say we were in selective oxidation, CO oxidation, but now, let's say, CO2 hydrogenation. Now it's very relevant, CO2 hydrogenation to fuels and to chemicals. And we were looking at CO2 hydrogenation to methanol. And we wanted to understand why the strange activity of gallium promoter to copper, because everybody knows zinc, it's always a good promoter, it's increased the selectivity for methanol. But for gallium, it was not so many research, and the research was quite contradictory. So it was not clear what, why for some catalysts, let's say the activity was very high and for some was nothing special. And so in this work, we let's say this was done by the PhD student Jan Alfke in the collaboration with a group of Christophe Copperet at ETH. So in the group of Christophe Copperet, they have very nice method for synthesis of the catalyst. Well-defined materials, not really catalyst. I would say it's like a model catalyst for, let's say, model powder catalyst. This, the methods they used were grafting on specially activated silica, gallium and copper precursors in controlled quantity to get bimetallic nanoparticles of copper gallium with a fixed, with a known copper gallium ratio, which was confirmed by PEM studies. And also we measured copper metal distance, so we could see that the concentration of gallium is controlled. We could get it under control. So we prepared these materials, which were also probably on the surface were partially oxidized. Therefore, I wrote here why, because let's say oxygen, because this oxygen could not be, some oxygen could not be removed by anything. So there were always cationic gallium also present. But the interesting thing that on this catalyst, which had a similar particle size, it was observed that at low concentration of gallium, the activity for methanol was strongly promoted. You can see it on this plot, but while the concentration of the fraction of gallium was exceeding 10%, it was going down. So the catalyst was becoming less active. And we wanted to understand why, let's say, the activity goes down, and we used all available techniques, let's say X-ray absorption spectroscopy, and I will show you also infrared spectroscopy, to understand what is the difference in the structure of this catalyst. While this gallium can have a role of promoter, but also kind of poison, why it makes the catalyst for methanol inactive. So while using X-ray absorption spectroscopy, we could detect that copper in this catalyst under catalytic condition at 20 bar pressure is always metallic. While gallium oxidation state, it's it's variable. In the catalyst, which is more active, the variation of the oxidation state of gallium was stronger depending on the condition. While we pretreated, when we added, let's say, CO2, then again removed CO2, we could see more variation of the oxidation state of gallium. But it was 33% and the catalytic condition of cationic gallium is 33%, and the rest was metallic. In the case of Poisson catalyst, was also mixed oxidation state, but more cationic gallium. Basically, okay, we could see that redox activity was somehow of gallium was changing, and also, or let's say, we did also experiments where we, on purpose, we also did experiment where we transient experiment where we were periodically removing CO2 and leaving system in hydrogen to pick up it even better. That more less active catalyst, it contained more cationic gallium, but also less redox active, and more active catalyst, it was more redox active. So this is the let's say what we could see with XAS. Then we went to, let's say, the maximum we could get from XAS, which we could not still understand exactly what's going on. We decided, let's use a drifts, infrared spectroscopy, and look if we see different intermediates, what's going on with the catalyst. And we also did design this cell, which can also go to 20 bar. And in collaboration with David Eferi, we used his spectrometers at PSI to use this cell. We look at three catalysts. The catalyst just containing copper nanoparticles, the catalyst promoted by gallium, and the catalyst poisoned by gallium. And what we could see that the catalyst poisoned by gallium didn't show any intermediates. The catalyst containing only copper, it was showing both formate and methox intermediates. And the catalyst promoted, it was showing only methox intermediate. So why we could not see formates? Because probably the mechanism of transformation of formates into, let's say, into more products like methoxy species is accelerated, so we could rationalize it. It was also very surprising that there were completely no intermediates for the catalyst which was poisoned, but somehow it also correlates that it shows no activity. It could not show anything, not even half product, like really nothing at all. And therefore, we came to the idea that most probably this poisoning is related to the formation of some shell around of gallium, let's say, gallium OX shell, which completely deactivates this catalyst. We still would like to confirm it with the theory and with also TEM, but this work is in progress to understanding it more from the theoretical point of view and maybe from imaging point of view, because XAS is a very nice technique to pick up the quantity of each state, but where these states are really situated, this is a limitation of this method, and here therefore we need imaging and theory. Yeah, just to show you maybe just a couple of examples, what we are now working on. So we would like to push the limits of the pressure, for example, studies of high pressure reactions with X-ray absorption spectroscopy. So this cell, which is already built, we are planning to use it for CO2 and CO hydrogenation, and it can, let's say, we can load in this cell up to, let's say, around 100 milligram of catalyst, and it can go to 50 bar pressure and 500 degrees Celsius, thanks to glassy carbon windows. And the idea is to do the structure activity correlations already now with GC, because for GC especially, we need to put a bit more catalyst to be able to detect the products, because sometimes it's the conversion is not so high, especially when we make our model catalyst and not the still industrial catalyst. So this is, let's say, in which direction we are going. And also, I think maybe it can be interesting for people who are doing more surface science. This cell we designed to do grazing incidence XAS to be able to be surface sensitive. And with this cell, we can measure XAS like really on the surface for the materials with equivalent to like 1 monolayer loading. So here this cell, it was designed by Sumant, and this cell within EU project on the model CO2 hydrogenation catalyst based on physically made nanoparticles, let's say, made from the cluster source. And this cell can go also to 20-30 bar pressure and the temperature up to 500 degrees Celsius, measure, let's say, the catalyst with such loading, measure high quality XAS. You see what kind of loading, 2.4 microgram per square centimeter. And this is the only thing, of course, this cell, it has about 20 milliliter volume. So we cannot classify it as an operando cell because we need another cell to be able to properly quantify the conversion with this type of catalyst. We could not find yet idea how to do it in the same time and the same place. Okay, so just to summarize, let's say what is unique opportunities of XAS for catalysis. I think I was trying to show you that we could, let's say, could really find the descriptors of the of catalytic activity. What are the main part for catalysis? Distinguish active species from spectators, but also really detect reaction intermediates, and they ultimately design, understand, and rationally design the catalytic materials. Yeah, so, and another thing, my talk was mainly focused on thermal catalysis and heterogeneous catalysis, but the technique is not limited to it. We have also cells and ongoing research on electrocatalysis, photocatalysis, homogeneous catalysis. And this is also, let's say, what are the people in our group at PSI. So it's a group of PIs who work in different fields. And if you work in certain field, you can think to whom you can, let's say, address if you would like. So there are people working more with electrocatalysis or with the photocatalysis, also microfluidics. And we develop cells, and we are also actively looking for collaborations to do interesting research together. Thank you very much.